Today we're going to be talking about how to find the limit of a multivariable function, or if the limit does not exist, to state that it does not exist. And in this particular problem, we've been asked to find the limit as xy approaches 0, 0 of this rational function x to the fourth minus 4y squared divided by quantity x squared plus 2y squared. So finding the limit here is going to be similar to the process we used to find the limit when we were dealing with a two-dimensional function. Remember that when we had a two-dimensional function, we would look at the left-hand limit and the right-hand limit. If they both existed and they were equal to each other, then we knew that the general limit existed. And we're going to follow the same process here, except that because we have a multivariable function, we have to look at the limit as we approach the point 0, 0 from different directions. So for example, if we have the point 0, 0, let's just draw a quick sketch here. If we have the point 0, 0, and we're approaching this point, right? We're approaching this point, we've been told that. We can look at how we approach it from different directions. So we could look at the value of the function as we approach this point along the y-axis. We could look at the value as we approach along the x-axis. We could look at the value as we approach along the line y equals x, right? Which is right here. So we could come at it from this direction. What we're trying to do is show that one of these two directions gives us a different answer than the other direction, right? Because if we find that the value of the function as we approach, for example, along the y-axis here, is different than the value we get as we approach along the line y equals x, then we know that we can approach this point 0, 0 from two directions and get two different values, which tells us that the general limit does not exist. We can have limits in specific directions, but the general limit doesn't exist. The general limit can only exist if the function approaches the same value no matter which direction we approach from. So we really have to show that as we come in here on the line y equals x squared, as we come in on this line, as we come in on this line right here, as we come in on this line, we always get the same value. And the only way we can really do that is by using the precise definition of the limit to show it. Right now, what we're going to try to do is find two different values of the function as we approach along different lines. So here's how we're going to do that. Typically, we start by approaching along the y-axis and along the x-axis. If we still get the same answers there, then we'll try approaching along the line y equals x here, or just along some line y equals mx, like this one that we drew here. If those give us the same answers also, we can try some different lines too, and if we keep getting the same answer every time, then we can go to the precise definition of the limit, which is more complicated, to really prove that it approaches the same value no matter where we approach from. But right now, we're just looking for one of these lines to give us a different value. So when we're talking about approaching along the y-axis, when we're talking about coming in from this direction right here, approaching along the y-axis, if we're approaching along this line, everywhere along this line, x is equal to 0, right? X is equal to 0 everywhere along the y-axis here. So what we do is we say we take the limit as 0, comma, y approaches 0, 0. So x is 0 everywhere along the y-axis. So 0, comma, y approaching 0, 0 means we're coming in along the y-axis right here, approaching this point at the origin, 0, 0. And what that allows us to do is plug 0 in for x everywhere in our function here. So plugging in 0 for x, we're going to get 0 to the fourth, or just 0. And so we're just left with negative 4y squared in the numerator. So negative 4y squared. In our denominator, we're going to get 0 squared here, which of course is just 0. We're going to be left with 2y squared only, 2y squared. Obviously, our y squared terms are going to cancel, and we're just going to be left with negative 2 because negative 4 over 2 gives us negative 2. Okay, so that's the value we get as we approach along the y-axis. What if we approach here along the x-axis? Like this, right? We're approaching that point at the origin, 0, 0, approaching along the x-axis. Well, as you might guess, that's just the limit of x, comma, 0 approaching 0, 0 like this, because everywhere along the x-axis, y is equal to 0. So this says we're approaching along the line, which is the x-axis here. So again there, we're plugging in 0 for y, which is just going to leave us with x to the fourth in the numerator and x squared in the denominator because this negative 4y squared and the 2y squared go away when we plug 0 in for y. Obviously, when we simplify this here, we're going to get x squared, because x to the fourth over x squared gives us just x squared. So we're left with x squared here. Well, what did we say? We said that as x0 goes to 0, 0. So that means x is approaching 0. So we plug 0 now in for x, and we get 0 squared, or just 0. The reason we didn't plug in 0, 0 up here is because we just ended up with a constant after we simplified, so there was nothing left to plug into. But here we ended up with an x squared, so we had to plug in the point 0, 0 to get 0 squared, or just 0. So what we know now is that as we approach along the y-axis, we get a value of -2 for the function. As we approach along the x-axis, we get a value of 0. So because the function is approaching two different values at this point here, 0, 0 at the origin, and -2 is not equal to 0, we know that the limit at 0, 0 does not exist, and does not exist there is our final answer. If we had come up here with -2, then we might have wanted to try a couple other values as well, approaching the origin along these different lines here to see if we could get any value to be different, right? But if we kept ending up with -2, -2, -2, -2, -2 everywhere, and this value looked like it was really going to be -2, then we would move on in our process to the precise definition of the limit to really prove that the value everywhere was -2. Because in order to prove that the general limit exists, we have to show that the function approaches the same value no matter which direction we approach it from, and we can't test at an infinite number of values, so we have to go to the precise definition to show that the limit exists. But for now, because we've shown that we have these two different values, we know that this particular limit does not exist.